Hello everyone, this is Mr. Sorrentino again, presenting another one of these videos for Math 31. This one dealing with 6.2, the systems of equations in three variables. Although they should probably say three or more variables, because I think they do try to throw a four equations with four unknowns situation at you in some of the homework problems. Because basically the procedure that we used in the first lesson in chapter 6, these methods work with also system of equations where I have three variables with three unknowns. Um, and so basically, as long as I have the same number of equations as I have unknown values, I'm usually pretty good and either going to be able to find that they do have a solution in common or that they don't. They don't have a solution or may have infinite solutions. Who knows? One of the issues tends to be, though, as we try to solve systems of equations at three variables, we don't have the option of graphing them because it would be a three-dimensional line graph, which is kind of hard to do on two-dimensional paper. And although some TI-84s may have the three-dimensional grapher feature on it, it's not necessarily going to be very useful, and it doesn't really have a tracing function anyway. So you would be out of luck to use that to find the intersection point, other than following along and seeing what the coordinates are. So we would have to use algebraic methods. It's just that they're more time consuming the more variables you have to solve for. Because when I look to do situations like this, there might be some substitution I could do along the way, but you're going to see more often than not that elimination tends to work best for this because of the fact that I'm going to have to get rid of one variable at a time. So I'm going to have to choose a variable to eliminate and then get equations written with those two variables, with that variable eliminated and the two others left, and then go through and do procedures to eliminate a second variable and solve for the one that's left. I'm going to demonstrate that on this system for this one, and then I'm going to let you have a turn for the word problem part, for example 2. So let's see what we can come up with here for solving this. As I go through this, I'm going to note these equations as equation 1, equation 2, and equation 3. Now, I'm doing some overkill on this. I probably wouldn't normally label them as such, but and be having labels about which ones are which and things like that. I just want to kind of demonstrate, how I'm going about solving this and to realize that there are variations that I can do with this. When I look at my x's, my y's, and my z's, I see that the y's, two of the y statements have a 1 in front, some of them with opposite sign, negative signs, one with a positive. The other one has a 3 in front of it. Whereas I look at the other ones, the x's wouldn't probably be too bad, 2, 4, and 1. I could probably deal with those if worse came to worse. And if I was dealing with the Z's, I'd probably have a little bit more issues with those because although the 2 and the 4, I mean, the 2 does go into 4, 3 doesn't go in either one of them, and 2 doesn't go into 3, so there would be some more work to do if I tried to eliminate the Z's. So I chose to eliminate the Y's. So I'm going to eliminate the Y first. For me to do that, I'm going to have to do combinations of two of these equations at a time. So I'm going to have my first one be 1 and 2. I'm going to try to start going through and solving that system. And the other one's going to be 2 and 3. Now again, these are what I chose. I could have chosen to do 1 and 3. Matter of fact, it might be a little easier in some cases. I'm just going to try to show you that there's different routes you can go. As long as I pick like a combination of two of them and I have two different combinations. Now, obviously one of them is going to get used twice in one of these, more than likely, and that's okay. I'm just trying to find ways of relating two of the equations at a time together to eliminate a variable. And so if I take the 2x minus y plus 3z equaling 7, and the 4x minus 3y plus 2z equaling -2, and I make that my system. Well, for me to eliminate the y's, I want to get the same number in front of the y's with opposite signs. And I can accomplish that easiest by multiplying both sides of that equation by a -3. That's going to give me a plus 3y on top and a minus 3y on the bottom. They will cancel. But remember, I just can't change the one variable I'm looking for, and that's it. I got to change the entire equation accordingly. And so this equation, this system, is going to become a -6x plus 3y minus 9z equaling a -21. This one's going to become 4x minus 3y plus 2z equaling -2. And then when I add these two together, I get a -2x. The y's cancel as designed. Minus 7z equaling a -23. And if I want to make it a little bit nicer, I can get rid of all the negatives just by multiplying both sides by -1. And I would get 2x plus 7z equals 23. Now that's not usually what we're used to getting to when we do elimination. We're used to getting a single variable equation and I could solve it and figure out what the number is. But remember, I have 3 different variables I have to account for here, so I'm taking care of getting rid of the y's on this one. So I'm going to call this one here equation A. This equation is yet another equation that should have the same solution as the first 3 did. So whatever equation, whatever values x, y, and z are supposed to be, and whatever solution they're going to have, this one should have the same one as a solution. When I do 2 and 3, now remember, we're here to eliminate the y's again. So we're still eliminate y's. So what I want you to do is carry through the elimination process on this and tell me what you get as a final equation. So again, I want to eliminate the y's, so that's why you have to make that decision first, because you have to eliminate the same variable out of both of these combinations. Otherwise, you're not going to progress anywhere. You're going to have one equation with an x and a y, the other one with like an x and a z. That's not going to do any good. So I'm still going to eliminate the y's, and the best way for me to do that, the easiest, is to multiply both sides of the equation by 3. I already have opposite signs on the y's. I just need to get a 3 in front of that y. So my system for this one becomes 4x minus 3y plus 2z equals -2. Nothing happened to the top equation. And I'm going to have 3x plus 3y minus 12z equaling a -21. And when I add them together, I get 7x. The y's cancel again. They should. That's what I was designing it to do. Minus 10z equals a -23. And I'm going to call this equation B. So I took the situation that I have now, where I had 3 equations with 3 unknown variables, and now I've come up with 2 equations with only 2 of those unknown variables that would have the same solution as those. So what I need to do now is take A and B together. So A and B as a system. So 2x plus 7z equals 23. 7x minus 10z equals a negative 23. And I want to solve this system. Neither one of them is particularly good for substitution. I would start getting, some decimals and fractions that wouldn't be easy to work with if I solve for any of the variables. I mean, our best case scenarios would be either to solve the top equation for x and deal with halves, or solve the bottom equation for z and deal with tenths, which are nicer to work with than working with sevenths. So there's things you could do for it. I'm going to still choose to do elimination, although that's not going to necessarily be much easier because of the fact that 2 does not go into 7, so, and they don't really have any common factors. So if I'm going to choose to eliminate the x's, I'm going to have to change both equations. And if I do the same thing with the z's, the only thing I would possibly save in the long run is multiplying one of them by a negative, because I already have opposite signs on the z's. But since that's the one that's going to be probably the least complicated, so choosing which one, either the 2x or the 7x, to be multiplied by -1 and then multiply everything by -1, making sure to distribute it correctly, I chose to leave the signs alone, and I chose to eliminate the z. Or did I? Yes, I chose to eliminate z. So the top equation, I'm going to multiply by 10. And the bottom equation, I'm going to multiply by 7. And so when I do that, I get 20x plus 70z equals 230. The bottom equation becomes 49x minus 70z equaling a negative 161. When I add the two equations together, 20x plus 49x is 69x. The z's cancel, as they should, because that's what I chose to eliminate. 230 plus a negative 161 is 69. Dividing both sides by 69 means that x equals 1. So I got one of the variables solved. Now what I'm going to do is come back to either one of these two equations, the a or the b. Since I have x and z only, I could put the x in and figure out what z is. So I chose a. So substituting in for x, I'm going to have 2 times 1 plus 7z equaling 23. So 2 plus 7z equals 23. Subtracting 2 from both sides, I would have that 7z equals 21. And dividing both sides by 7 would mean that z is 3. So now I know the value for x, I know the value for z. Now I had to go and figure out what the value of y is. And so I go back to up to one of these original 3 equations. Doesn't matter which one I choose. I so happen to choose the very top one. 2 times x, which we now know is 1, minus y, which is what I'm looking for, plus 3 times z, which we know is 3, should equal 7. So I have 2 minus y plus 9 equals 7. So 11 minus y equals 7, which means y would equal 4. So my solution, which we'd write as an ordered triple, and always alphabetical order, so x, then y, then z. And that'd be the solution for this. Or of course you could just indicate these, just make sure that you indicate what they are. Maybe even summarize it and put it all together, but that would be your solution. So you could see This takes a good bit of strategy. It takes a good bit of thinking your way through it, making decisions, and it involves a good number of steps. If there are methods that have less steps, it would be better to learn them, because if there's more steps, there's more chances of just making just some random computational mistakes, But of course, obviously, if there's methods that require less steps, that requires you to know different methods. So it's a give and take here. And most of the rest of this chapter is going to be dealing with ways for you to uh, that are less involved in this, or at least less overall steps that have to be taken to solve a system of equations like that have three variables or more. So as we get into 6.3, 6.4, 6.5, 6.6, not so much 6.7, we get into those particular chapters or those particular sections, we're going to learn methods that take situations that help whenever I have, more than three or more variables that I have to figure out the solution um, to solve a system of equations. Whereas if I have just, two equations with two unknowns, I could probably just use elimination or substitution. It would probably be just as easy than using the other methods, although the other methods will work on those too. So let's have a look at the word problem. And of course here, you know, at the bottom of your notes, I have a disclaimer that's saying that, we're learning other methods here as we go through this to go through and answer find better ways of solving for a system of equations like this. Okay, example 2. I'm going to have you do this in 2 different parts. So the first part, let's go read the problem here. And Casey receives $190 per year in simple interest from 3 accounts she has. So we're not going with exponential or compounded interest. We're just doing simple interest. The 3 accounts pay 2%, 3%, and 4% simple interest respectively. Casey had 3 times the amount of money invested at 4% than she invested at 3%. Find the amount of money invested in each account if the total amount she invested is $5,875. So the first thing here, and I'm going to start you off, is we want to find the amount of money invested in each account. There was 3 accounts, so I'm going to let X equal the amount of money in the 2% interest account. And of course the others are going to be. So what we need to do is come up with 3 equations that relate these 3 unknown values together if I'm going to have any hope at all of solving this system. And so you're going to be asked some questions, and using X, Y, and Z defined this way, these questions that you need to answer are going to help you develop the 3 equations you're going to get. So answer these 3 questions, and then we'll go through this. Okay, so the first one I'm going to write here is the total amount she invested is $5,875. That's the easiest one there, because the total amount she invested would be the sum of these 3 accounts together, the original values of each one. So that means that would be X, Y, and Z added together. So that system of equations from that information would be X plus Y plus Z equals 5875. The second one I'm going to deal with and write an equation for, it tells me that she earned $190 per year in simple interest from the 3 accounts, and we know what their amounts are. Well, for me to calculate the interest she earned in each account, I would take X times 2% of that, and that'd be the interest she earned in that account. And for Y, I'd take 0.03 times the amount she invested there. And then, the third account, take 4% times the amount she invested there to find their respective interests, and I would add them together. So that means that 0.02x plus 0.03y plus 0.04z is going to equal $190. So again, each one of those terms is the amount of interest she earned in the respective account, and then you take the amount she earned in each account, add them together, you get 190. So that's where this one comes from. The last one comes from Casey had 3 times the amount of money invested at 4% than she invested at 3%. So that means they're telling us a relationship between the variables y and z. X has nothing to do with that statement. They're not mentioning the 2% account at all, so they're saying she has 3 times the amount of money invested at 4% than she did at 3%. That means that the amount she has at 4%, which is z, is equal to 3 times the amount she has invested in the 3% account, which is y. So we know that z equals 3y is the third equation. There's my system. And to rewrite them, because maybe I don't like having the decimals so much in the second equation, I can multiply the entire equation by 100 and get 2x plus 3y plus 4z equals 190 with 2 more zeros, so 19,000. And I just multiplied both sides by 100, and z equals 3y. So there's my system of equations for this. So let's move over a little bit. Now we want to solve this. So what I want you to do is now take this system of equations and solve it and see what you come up with. Okay, so again, as I go through and show how I went about doing it, your method may not have been exactly the same. So you might need to check through to make sure you're checking your calculations and everything along the way. But what I chose to do first, this made getting down to one variable really easy. I chose to use the fact that we had an equation that said z equals 3y. That means I could basically eliminate the z's from the two equations up there. So this one can be rewritten as x plus y plus 3z equals 5875. This one could be rewritten as 2x plus 3y plus 4 times 3z, or take that back. I should just say 3y. I think I said 3y and wrote z. 4 times 3y equaling 19,000. And so when I simplify these two, I'm going to have x plus 4y equaling 5875. And I'm going to have 2x plus 4 times 3y is 12y. 12y plus 3y is 15y. That's going to still be 19,000. So this is the system of equations that I have to solve here. If I want to use substitution, I could solve the top equation for x pretty easily without getting any weird fractions or decimals involved that could complicate my calculations. Even with that, though, it's also pretty easy to use elimination to eliminate the x first and solve for y. And I could do that simply by multiplying the top equation on both sides by -2, because that would make the top a -2x, the bottom would have a positive 2x. When I add them together, they would cancel out. And so my system would become -2x minus 8y equals a -11,750. The bottom equation was untouched with my methodology. Again, if you chose to go different routes, that's fine. Just sometimes you might give yourself more computations to do as a result. So, I mean, look for the easiest route to go, but it does take some experience and practice to start being able to recognize that more regularly. When I add the two equations together, the x's do in fact cancel out. That's what I wanted them to do anyway. When I add these two together, I get 7y. And this here, I get 7,250. When I divide both sides by 7, I get approximately $1,035.71. Now I could use the fact that z equaled 3 times y and just multiply that by 3 to get that z is approximately equal to $3,107.14. And then I could use these two values along with this equation and come up with that x plus $1,035.71 plus $3,107.14 should equal $5,875, which would be x plus $4,142.85, equaling this. Subtracting $4,142.85 from both sides, I get that x is approximately equal to $1,681.15. And so my final statement to answer the question based off of this information would be this. So she invested $1,681.15 at 2% simple interest, $1,035.71 at 3% simple interest, and $3,107.14 at 4% simple interest. And there's the answer to that. So you can solve systems of equations using elimination and substitution. It's just that if you have more than two equations with two unknowns, you have to kind of whittle it down. You have to eliminate one of the variables in some way first, and then eliminate another variable until you get down eventually to somewhere you get just the equation with only one of the variables in it. Then you can use all those intermediate steps to figure out what some of the other variables are. So obviously, the more equations, the more variables you're looking for, which means the more equations you're going to have as well, the longer this process could take. And so again, that's why we start learning in 6.3, 6.4, 6.5, and 6.6 that there are other methods that you can use to solve systems of equations, particularly if you have three or more variables involved. A little bit more of a streamlined procedure than what this would be. But that brings me to the end of this video. If you have any additional questions, please make sure to bring them up during class or come and see me during my office hours. Until I see you in one of those places or until the next video, I'll say goodbye and have a good day.